All right, so here we go. Third video for section 7.5, conditional probability. We're going to start with the product rule. The product rule is a direct consequence of the conditional probability rule. The conditional probability rule said that the probability of E given F was equal to the probability of E intersection F divided by the probability of F, but with a tiny bit of algebra that can be turned into the probability of E intersection F is equal to the probability of F times the probability of E given F. That is, if you know the conditional probability and a singular probability, you can use those two to find an intersection probability. And then depending on how you define this one over here on the left, like if I switch this and call this F given E, that numerator stays the same, but the denominator becomes an E, which means then that the probability of E intersection F could be also found by taking the probability of E times the probability of F given E. Depending on which of those two you know, you can find that intersection. Now, what does this mean for us? Well, it actually means something nice because it gives us a formula, but we can also relate this back to, I'm going to go back up here, these tree diagrams that we were working with earlier, right? And what I'm going to do is I'm going to erase here, and I'm going to draw in a tree diagram to show you what I'm talking about. Now, our standard tree diagram for the conditional probability scenario would start out like this. There would be some event E that either occurs or does not occur that has some known probability. So this branch right here would have the probability that E occurs. This branch would be the probability that E does not occur. And then conditional probability comes into play. And these next branches would be about F happening given that E happened, or F not happening given that E happened, or F happening given that E didn't happen, or F not happening given that E not happened. And then each of those branches would have a conditional probability. This would be the probability of F given E. This would be the probability of F not given E. This would be the probability of F given that E didn't happen. And then down here, this would be the probability that F didn't happen given that E didn't happen. And what the product rule tells us is to get here to the end means that you're looking at E and F both happening, or the probability of E intersection F. But what it means is we just need to multiply down the branch. If I just multiply down the branch, I'm going to take E times F given E, E times F given E, and that's going to give me my intersection. In fact, every one of these terminal branches over here is going to be an intersection. This one down here is the probability of E didn't happen and F didn't happen. This one's the probability that E didn't happen and F happened. This one's the probability that E happened and F didn't happen. And if you were to multiply down any branch, you would get that intersection. All right, so let's see if we can make some sense out of this. Let's take a look at an example here. All right, so here we go. This is going to be an example that's going to try to tie in that product rule. A bicycle factory runs two assembly lines, line A and line B. If 95% of line A's productions pass inspection, while only 85% of line B's production pass inspection, and 60% of the factory bikes come off assembly line A, the rest come from B, find the probability that one of the factory's bikes did not pass inspection and came off the following blah, 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 blah. Before we go any further, I just want to point out something. Did you read that and hear that means conditional probability? That's the probability that something passed inspection given that it came from line A. So that's conditional probability. Oops, I didn't want that. That's conditional probability. So if we say that I means pass inspection, then that's the probability it will pass inspection given that it came from A. Similarly, that's conditional too. That's the probability it will pass inspection given that it came from assembly line B. All right, so let's keep working here. They want me to find, or they want us to find, the probability that the bike did not pass inspection and came from the following assembly line A. So what they want us to find is, they want us to find that it came off of and did not pass. So this is not a conditional. This is did not pass inspection and came from assembly line A. That's a conditional probability, or is that an intersection? That's not conditional. That's not the probability that it didn't pass inspection given that it came off of line A. It's I picked a bike from the pile at the end. What's the probability that it failed and came from A? Now me, I'm a big fan of visual things, so I'm going to draw out a tree diagram to help me understand this. Now first things first, when bikes are made, they can either come from line A or they can come from line B. Okay? 60% of the bikes come from A. That means that the remaining 40% come from B. Now, once a bike goes down an assembly line, it can either pass inspection or it can fail inspection. But these are conditional, remember? It's conditional that it passed inspection or failed inspection given that it came from A, or that it passed inspection given that it came from B, or that it didn't pass, failed, given that it came from B. Now we know a couple of these probabilities. We know that this one is 0.95. We also know that this one is 0.85. But what about these two probabilities? Well, if 95% pass, 5% fail, and if 85% pass, then 15% don't pass. I don't know, do you want to call it fail? Do you want to call it don't pass? I don't really care. It's inspection passed or did not pass inspection. Okay. Now, if they want me to find didn't pass inspection and came down A, that means I want to get to here. That's going to be the branch where in the end you failed the inspection and you came from A. And so the way that I'm going to find that is I'm going to use the formula that says that this is the probability of A times the probability of failing given A. It's the two branches here. It's going down this branch and then going down that branch. All right? So that's going to be that 0.6 times that 0.05. And that's going to give me, let me grab my calculator. I drag this over here to the side here a little bit. So 0.6 times 0.05, and I get 0.03. Well, we've got about not even about, a 3%. There's a 3% chance that if I grab a bike from the pile of bikes after they've been built, that bike will be a bike that failed inspection and came from line A. What about if they wanted it to come off of assembly line B? Well, it's roughly the same question. It's just saying, what's the probability that you didn't pass inspection and you came from assembly line B? Well, the formula says that that's going to be the probability of B times the conditional probability that you failed inspection given that you came from. Geez, that is an ugly B. You think it's a letter in my name, I'd know how to make it. Okay. So on the tree diagram, that's going to be B and then failed. So that's going to be our 0.4 times our 0.15. I'm going to grab my calculator. 0.4 times 0.15, and I get 0.6. No, 0.4 times 0.15. 0.06, that looks better. And so I get 0.06 or 6%. So if I grab a bike at the end, blah, 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 blah. Right? Now what they want us to do is they want us to find the probability, this is number 50 now, find the probability that one of the factory's bikes did not pass inspection. Okay. So this is just the probability that if we grab a bike, it doesn't pass inspection. Well, here's what I know so far. I know that this branch right here, this one in purple that I've got up there, that one worked out to be, and I'm going to erase this so I have a little bit of room, worked out to be 3%, which means that this one is going to be 6%. Okay. These two then would be the rest, and I don't know what they are, but I do know that all four of these numbers have to add up to 100% because they are all the possible outcomes for this experiment, and the sum of the probabilities must add up to 1 or 100%. Everyone will look at that. And so I've got a 6% up top, I got a 3% down bottom, so I have a 6% plus a 3%, which means we've got a 9% chance, or a probability of failing inspection is 9%. Right. We good there? If you are uncomfortable with that, do a numerical thing. Put 1,000 bikes into this and see what happens. You'd get 600 that end up here, you'd get 400 that end up here, you get a bunch here that passed, a bunch here that failed, a bunch here that failed, a bunch here that passed, and you could do this numerically if you wanted. Because once you've got the tree diagram, if you're uncomfortable with the probabilities, run some people through it and see what happens. This leads us to something called independent events. Independent events, okay, so two events, the event E and the event F, are said to be independent if the outcome of one of the events has no effect on the conditional probability of the second event. Right? So E and F are independent if this is true or if this is true. So what did that say? Well, let's take a look at what this one says. This one tells me that the probability of E happening, given that we know F occurred, is just the probability of E. So whether F happened or didn't happen or whatever, F's existence doesn't matter because the two events are said to be independent. Okay? This one over here is saying that E doesn't matter because the two events are said to be independent. So when we're finding whether two things are independent or not, what we're going to check is we're going to check to see if the conditional probability is different from the plain old probability. Now, a super, super easy way to think about this is, imagine I'm picking two cards from a deck. And each time I pick a card, so I replace that card in the deck. So when I pick a first card, and let's say that this is the first card red, and we'll say that B then is the second is, I don't know, let's make it be a face card. The probability that the second card is a face card, given that the first card was red, is just the probability that the second card is a face card, because if I put that back into the deck, then it doesn't really matter whether I picked a red card or a black card or a face card or a 2 or a 9 or anything, because when I put it back in the deck, it ends up being irrelevant to the outcome of the second pick. So those two events, we would say that those two events are independent events, because how the first card turns out has no effect on the second card. Now that's a pretty straightforward example, and I think that most people would look at that and go, yeah, that makes perfect sense. Let's take a look at a slightly more complicated one. In a certain area, 15% of the population are joggers and 25% are overweight. If 65% of those who do not jog are overweight, find the probability that an individual fits the following descriptions. An overweight jogger, a person who is not overweight and is not a jogger. An overweight person. Are the events that a person is overweight and a person is a jogger independent? Okay, so let's see if I can make some sense out of this. I'm going to go back to the problem and read it more. Okay. In a certain area, 15% of the population are joggers. Okay, so that's a probability. 25% of the joggers are overweight. Okay, so that's a conditional probability. So now I know I've got a scenario like this. I've got people who are joggers, and I have people who are not joggers. I know that there's 15% of the population who are joggers, and that means that there's 85% of the population who are not. And then I've got the conditional probability of being overweight given that you're a jogger, or not overweight given that you're a jogger. Overweight that given you're a jogger is 0.25. So that means there's a 0.75 down there, right? Overweight given that you're not a jogger, or not overweight given that you're not a jogger, right? Let's see. 65% are overweight, but okay, so then this is 0.65 because it's the overweight given that you're not a jogger, and then this would be 35. Right? Let's take a look at what they want us to find. I got my tree diagram all filled out. Right? Here, this is jogger intersection overweight. Here, this is jogger intersection not overweight. Here, this is not a jogger intersection overweight. Here, this is not a jogger intersection not overweight. Right? In part A, they want me to find the probability that someone is an overweight jogger. That is, the jogger intersection overweight. All right, so that's that first branch. So that's going to be the 0.15 times the 0.25. So I'm going to grab my calculator. 0.15 times 0.25, and I get 0.0375. All right. The second one's asking me for I'll use a different color. How about orange? A person who is not overweight and is not a jogger. So the probability that someone is not a jogger and not overweight. Let's see, that's going to be the last branch. So that's going to be 0.85 times 0.35. And so let's see, that's going to be, okay, calculator. 0.85 times 0.35. I get 0.2975. Okay. Overweight. So overweight is this branch or this branch. Now I already know the top branch is 0.0375, so let's find that other branch. That other branch would be the probability that you're not a jogger intersection overweight. So that's going to be 0.85 times 0.65, which is 0.85 times 0.65. That's supposed to be 85 there. 0.5525. So then if I take that 0.0375, which was the overweight joggers, and add it to the overweight non-joggers, I get that the probability that someone is just plain old overweight is 0.0375 plus 0.5525, 0.59. Right? And now the question is are the events that a person is overweight and a person a jogger independent? Well, if the probability, let's see, independent means that the conditional probability is the same as the probability. So let's see. Are the events that a person is overweight and a person is a jogger independent? Well, if they are, then the probability of overweight should be equal to the probability of overweight given that you're a jogger, and the probability that you're a jogger should be the same as the probability that you're a jogger given that you're overweight. And so I'll check those two. Probability of overweight is 0.59. Probability of overweight given that you're a jogger was 0.25. 0.59 is not equal to 0.25, so no, they are not independent. Right? All right, this brings us to the end of 7.5. The next section is 7.6, and it's a doozy. So I'll see you all back here for section 7.6.